You're good.
Yeah, we didn't finish.
Okay, go back one.
The standard view.
Is that better?
That was at the end.
Yeah, that's where we did.
You need to zoom in on the bottom.
Yes, please.
Is that better?
Nice.
All right, couple more seconds as you guys try to finish that puppy up. From yesterday, we were talking about unit vectors. How do we take a normal, I should say that either, that has a math meaning. Do you know what normal means in physics? Perpendicular. Normal force is another name for the perpendicular force. Anyway, take a regular vector, there we go. Yesterday we learned how at the very end of vector, which this one had the components of 7, 5. Remember the side carets? The components of 7, 5, 7 being the horizontal component, 5 being the vertical component. This form, which is called component form, is a good form. It's very useful. However, sadly, this form only denotes length. Going 7, going 5, independent of showing little horizontal vectors and vertical vectors. Just length, that's what this form shows. Which in a way, if you go positive 7 and positive 5, you will end up headed the same direction as the vector v. But one perk to this bottom form, which is, we're going to call it, actually on the next page I think, linear combination form, or maybe a couple pages. Linear combination form, as you guys notice, it still has a positive 7 and a positive 5, which is another way of writing vectors that separates the two. 7 goes with the unit vector I. So if you think about it, what does that mean mathematically? Take that unit horizontal vector. I need to make that thicker. Hold on. Not that. Take that unit vector and say, hey, n times 7. So 1, 2, 3, 4, 5, 6, 7. There we go. And then we go up 1, 2, 3, 4, 5. When we multiply the I vector and the j vector by a coefficient, we are literally putting two vectors together and saying that v is the sum of this horizontal vector plus that horizontal vector. And that's legal, right guys? Because isn't this head to tail? Right? So it's totally legal. Just another way of expressing. Why is my bottom vector so much bigger than my top vector? Because I made the unit vector considerably larger than it was up above. So my unit vector was just a little baby unit I up above. And I made the unit a little bit bigger down there. But they're proportional, they're similar. So just a little precursor just before we change the page. It is still coming, but this is called linear combination form. Linear combination form. When you put the little i's and j's. So I was introducing a future idea. And what was this top one called again, real quick? What was this one called? Component form. Components are in the side brackets. The linear combinations show the components with an I vector and a j vector. But it basically means the same thing. Cool. And how did we find that unit vector again yesterday? Where did these numbers come from? Kind of the sines and cosines.
Oh, the proportion of the one, the standard unit.
Yeah. Take the bigger triangle, right? And then you're trying to make it proportional with a tinier, smaller, similar triangle. And how do you do that? You scale everybody back. So Sean was saying like sine and cosine. Yeah, basically. Because you can do opposite over, sorry, that's adjacent, isn't it? You can do opposite over hypotenuse. We're scaling back because the unit circle always has a hypotenuse of 1, a radius of 1. So you could think of the vertical component as sine, opposite over adjacent, hypotenuse. Man, my words are not working today. And you can think of the horizontal component as adjacent over hypotenuse. That works too. But we have to find the hypotenuse with Pythagorean, so we have to think about a triangle, and then we got to scale everybody back by division. Cool? see? Linear combination. I knew we were going to write about it soon. Linear combination. Shouldn't take us too long, because you guys just saw it on the last page, but hold on, careful of your notation. It's a bold I and a bold J. So how are you going to write it? Yeah. With a vector sign on top. You can think of it as array. Just be careful that you know it's not array, truly, right? Oh no, so the W, what are we going to do with him?
Put a
Yeah.
little arrow on top of it.
Grab a little arrow on him. Use a vector.
This is just for curiosity.
Yeah.
Is this probably like one of the hardest sections in the chapter?
Depends on whether you like physics better or math. If you like math, this might not be your favorite, but if you like problem solving and like real applications and stuff, then maybe it won't be too bad. However, some people, usually calculus kids in talking about pre-cal are like, vectors, but usually they're like, oh, but actually that was a pretty good grade on that test. So I don't know. But you do get to use your calculator on all of chapter 6. That's good, right?
Sure.
So then down here, we're still putting more vectors, right? They're all vectors, vectors, vectors. In your homework, when you're writing the directions in the problems, vectors, 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 right? Not every time you see a letter, but every time you see a bold letter. Are we tracking? So many little vectors. Don't you guys just feel smart when you make a vector? No. Some of you agree. So, two different ways of writing the W vector. The W vector could be written as, in component form, what and what? What would be my first component? 4. And what would be my second component? Bingo. If you're wondering why, make sure you go over and look at W and say, oh, I see. He ends at 4, -5, which means from 0, 0, you need to go right 4, down 5, hence our component form, right?
Why do we have 2 W's though?
Because now we're going to write it in our linear combination form. Is it that crazy hard? Nah. What coefficient are we going to put by the I? What coefficient by the J? And you can either do plus -5 or -5. Same dealio. So, wait a minute, hold on. Aw, man, we gotta do basic operations in linear combination form also? Yeah. But guys, was the math that hard before? It was the graphs that were hard, right? So the math, well, is the math going to be hard with components either? No. Can I zoom in? You guys ready? So how do I do 2U, oh no, sorry, 2B? Scalar multiplication. What's 2B equal?
About 6C minus 4J with the arrows.
6I minus 4J. Can we write it in components? Sure we could, but we don't need to. Number 2, go quick. Combine like terms, right? 4I, right? Because it's 1I since there's no coefficient. Yeah. 4I plus 3J. Oh, yeah. That would have made more sense. Remember, if there's nothing there, we see it as understood 1. Then find the unit vector. Can we do that without a picture? Sure. Let's do U, but let's put a little subscript of unit. The unit vector of U equals. Hold on, before we can do the unit vector, well, hold on. Wait. can't we start with 1 over plus 5 over? Can't I start there?
Yeah.
Because my vector is 1 and 5, so we could go ahead and do a quick little sketch and say, okay, so my vector, technically, if I was to show him for u, I would go over 1, I would go up 5, and we have vectors now since we're doing linear combinations. Okay, there's my vector u. I know my 1, I know my 5. What am I trying to find to scale back to have a unit vector, aka with the hypotenuse or the vector magnitude of 1? What do I need? Yeah, I need to use magnitude in order to get back to a unit vector. So what's the magnitude of, how do I show magnitude? Got it. Magnitude of u is square root of 26. Pythagorean theorem is as simple as that. So therefore, if I want to scale back, remember, to my unit vector, the guy I'm trying to solve for, square root of 26 is about 5, so we can say about 1/5. Right? That looks more like a 4th. Oh well. Probably should be a perfectionist. There we go. We divide everybody by 326. And we're getting ready for calculus, so stop there. Stick it to the man, we're done. But at the back of the book writes root 26 over 26, 5 root 26 over 26 will be good, right? They just might rationalize it. So, linear combinations. It's really just a new notation, right?
Yeah.
It's warm in here, I know. Hang in there. Anybody still getting it? A couple more seconds. Okay.
Is there a little bit of like similarity? Because that's the size has to go this.
Exactly. Or if we're trying to shrink, right? We're doing the opposite. So as we shrink all the sides, they're going to shrink by the same amount. And we need root 26 to go back to 1. So we're going to divide that by root 26, so divide everybody by root 26. So we have to divide this side, and that side, and that side. Yep, it's geometry applied. Let's go. All right. Direction angles. Wait, why do we have angles? Oh, that's right, because of magnitude and direction. Because of magnitude and direction. Now, kiddos, to be honest, in really complicated physics problems, you would love your vectors to be in component form or linear combination form. Actually, some physics classes might call linear combinations components because it's showing the horizontal and vertical as well. It's showing it in that we do have a horizontal length A and a vertical length B. You might not be able to see it, but I do have little arrows on each of these. In a complicated physics problem, it is best to be using component form. It is best to be using component form. But that doesn't mean that there is no application for direction because, for instance, if you're out on the ocean and you're trying to go a certain direction to a certain location, and it's not just dead ahead, aren't you going to have to turn an angle? You can't necessarily say turn left past the wave. That's not going to work. Right? On streets you can say, yeah, turn left past the, I don't know, what am I say? The gas station, turn right at the McDonald's, and then turn left at the, those of you that don't drive, you probably just have landmarks, not really streets down. Those of you that drive, you should be learning street names. Oh dear. So start using GPS and then realize what street you're on. You have to tell someone how to get to your house.
I don't tell them.
I don't use
Yes, I do this.
landmarks. That's how you do it.
But if you're on the water, but wait, if you're on the water, hold on. If you're on the water, are you necessarily gonna have to take this street and then take that street to get to this location from there? It would be nice. But if you're on the water, you're just gonna turn and you're gonna head, right? Unless there's like a hurricane. 15, then maybe don't do that. Besides that,
Sure.
I know, I'm in like Pirates of the Caribbean right now in my head. Anyway, angles can be useful. But how do we find angles? Well, kiddos, hold on. If we know the linear combination, aka if we know the components, how do you find an angle if you know opposite and adjacent?
Use trigonometry.
Use trigonometry. Can't we say tangent inverse of b over a is just equal to theta? So it's just trigonometry applied. It's not anything new. It's just like, oh, hey, with vectors, we'll find a direction angle just using a right triangle. With the horizontal vertical components, north and east or north and west are related by a right angle, yeah? Oh, I have it backwards. I know. Sad day. Solving for theta should go in that category, huh? Oh, I know. Close the info. It's okay. Do a sigh. Tell yourself Miss D is not perfect. Oh wait, none of us are. God is good. Let's return. Praise Him for the gospel. Message of grace. Okay. How do we solve for A and B if we know theta?
Well, it'd be.
Yeah. Well, kinda. Wait a minute.
You wait
Oh,
for the
yeah.
angles, right?
If I put a tangent, can I find A and B, or am I going to find B over A?
You're gonna find B over there.
We don't want to find B over A. We want to find A and B.
So sign it.
But you're like
use the magnitude.
Yeah, if they give you the angle, guess what else they're giving you? Because they have to tell you about the whole vector. They must have also given you the magnitude. Now, kiddos, if we know this piece, and if we know this piece, if we know hypotenuse, and if we know angle, how are we going to find A and B? Separately, exactly. We need sine. Sine of theta is equal to B over magnitude, right? So can't we solve for B and say B is always going to be magnitude sine of angle? Hypotenuse times sine? That makes sense, right guys?
Nice.
So how are we going to find A? Well, he's the adjacent, yeah? So we'll have A over magnitude of B. Solving for A, we have ourselves another formula. A equals the magnitude times cosine of the angle. There we go. What are these? Oh, I don't know, just, trigonometry. But what do they let us do? Go from magnitude and direction form to components, or go from components to magnitude and direction. Wait, why didn't I show the formula for magnitude? How do you find magnitude given A and B? Oh, we've already talked about that, haven't we? Magnitude is just Pythagorean theorem, square root of a squared plus b squared. So I didn't rewrite that one because we technically already wrote them down and figured them out. Could you memorize? Yes. In physics class, would you memorize? Yes. But is there a mathematical reason as to why, or really just make a triangle and solve it? Yeah. Then why in physics don't they show the mathematical background? Well, the physics problem has a lot of stuff going on, and they'd rather just kind of memorize lots of stuff to be able to use and not have to draw tons of pictures. Although, do you guys remember Dr. T? Was that before your time?
Dr. T.
Dr. T. When he taught physics, the kids literally had to take out rulers and protractors and draw vectors accurate to the units, the length they're supposed to be, and actually measure their bearings, their angles, and then show how to do vector addition and put it all together. So before memorizing all that extra stuff. It was pretty cool. All right. So, example, how do we put all this together? Find the component form of the sum of u and v with direction angles theta u, theta v. Then find the direction and magnitude of the resultant. I apologize, some of my spacing is off, but I can't really change it since this is just a PDF. As you guys are looking at this, what's the overall goal? We have two separate vectors, and what are they telling us to really do with them? Now, Once you have the problem, put your pencil down. I'll wait till you guys have it. Once you have it written down, pencil down. There's a geometric way to solve this, and then there's a algebraic way to solve this. Both of them need trigonometry, so that's what's kind of involved. There's a geometric way, which is the way I was talking about with Dr. T a second ago. And then there is an algebraic way. I'll show you the geometric, but it gets pretty complicated. So then we're going to write down the algebraic, which is simpler. Sound good?
Sounds great.
Sounds great.
Seeing that this angle would be 80,
Okay.
can you use the sine of this angle? No, it's not a right triangle.
Not a right triangle. It might be, it might not be. Know what I mean? Oh, it's 80. It's not right. If it was 90, yeah.
Yeah.
Except, hold on, there's one more problem, Luca. When we try to add, can we just connect them and say yay?
No.
Oh, I went too far. That's the problem. No, we can't connect head to head.
Oh yeah.
Must be tail to tail.
Mm-hmm.
Oh no, head to tail.
Head to tail, there we go.
Yeah,
So here's the struggle. If we wanted to find the sum geometrically. Go ahead and put pencils down. If we were to try to find the sum geometrically, we would have to go ahead and set this all up very accurately, which I tried to kind of do. The 51 is longer, the 31 is shorter. It looks kind of like 30 degrees and 110, right guys?
Yeah.
Kind of, sort of. Okay. If we were to do this geometrically, we would have to actually say, wait a minute, hold on. Here's our vector u. That's all well and good and all. But I don't want him there. I need him up here, right? Now is it head to tail?
Mm-hmm.
So where would the sum be? Here, right?
You have a. No, that's still not a right triangle.
Nope, still not a right triangle.
Um,
So if I wanted to find the magnitude and the direction of this guy, I would need to figure out his angle and his magnitude. Now, could I do that with geometry and trigonometry? Yeah. I could do something like, hey, parallel lines are congruent. No, not congruent, sorry. Parallel lines cut by a transversal. Remember this?
Ooh.
Have, Luca, didn't you say a second ago this guy's 80?
yeah.
Have interior angles on the same side adding up to, ooh, hey, guess what? This guy's 100. Oh.
Oh.
Well, if this guy's 100, can't we use law of sines, law of cosines to help us out to find the missing length and to find the
I'm
missing
never gonna see that though. Never. I'm
angle?
never gonna see that.
Yeah. How did you find that?
Because 180 minus 80 is 100.
Parallel lines
Parallel lines.
cut by a transversal. Angles on the interior of the angle add up to be 180. So since I took 110 minus 30 for the 80 down here, I was able to take 180 minus the 80, get 100 up there. Then we were able to say, okay, so that's 100. This guy is, oh wait, we haven't even found this guy yet. Who's this guy? We
You.
have to find that guy, right? So we don't know him. We have to find him. Once we find him, we can subtract
Wouldn't it
from
be 50
him
degrees?
to get him.
Oh, wait, Misty.
That'd be fun.
Misty, can we use like one of the laws because since u is equal to u, we can take the number 50, put it up
Exactly.
there. We have two
We have
sides.
side, we have angle, and we have side. We could use law of cosines. Side, angle, side. We could use law of cosines, and we could find who we're asking
Look at all that mess.
and who we're asking.
Look at all this. Like.
It's amazing. Look, it's geometry and trigonometry and physics all in one. All right, you can pick up your pencils now.
I said we did the
Look
other
at all that stuff.
But is it possible? Yes. However, let's go back to the original question and say maybe it's not so fun to go straight From, even though it's in direction magnitude form, maybe we don't want to stay in direction magnitude form. Remember how I said components are easier? Question, how can we write U in its components?
You gotta find the sign of 30.
Yep, we have to find A and B, right? Well, struggle, hold on. Weren't there formulas for A and B on the other page? Isn't it magnitude cosine angle for A? And isn't it magnitude sine angle for B?
Ooh.
Check it, check it, check it. Yeah. Because we have magnitude and direction. It's a whole lot easier to add when it's in components, right? Than to do all that geometry I just wrote. But we can't add with components until we get the components. And how do we get the components? From the formulas. Does that make sense? So then, coming back over, I plugged in one formula, A cosine theta, to be my horizontal component, A sine theta. Sorry, magnitude. Magnitude cosine theta to be A, magnitude sine theta to be B. Why is that so cool? What are we going to do with B? Same thing. The only time this is going to get hard is when you're working with bearings.
Oh, there were some of them.
Bearings.
Otherwise,
Yeah, that was a little interesting.
Bearings. Aww. Why are bearings hard? Remember from way back when? Do they measure from our normal positive x-axis up counterclockwise? No. Where do they measure from?
They measure from north.
Compass. They measure from north and they go east, or they go west, or they go southeast, southwest. Which is more practical, but then all of our angles are kind of in different reference systems and it gets a little bit harder. But if it's in standard position, this is easy cheesy, because all you gotta do now to find the sum is
Plug it in? No.
add. And remember, we don't want error. We don't want to have to find it and then round it and then write it again, then use it. Ew, gross. Can't we just add him plus him to get the I component?
Right.
And can't we just add him plus him to get the J component? Someone, please, in your calculator, you're working on this, right? Add the I's, add the J's. Don't give up.
Okay.
Make sure you're in degree mode. 50 cosine theta? No, sorry. 50 cosine 30 plus 30 cosine 110. What's I? People, look at you have a number on your screen. What is it?
I have J.
Oh, okay. What's J?
J 53.19.
Give me 3 decimals.
191.
Perfect. Who has I? Amanda, what do you got?
33.04.
Someone back each of them up. I just need to hear a yes if you agree. Say yes, I, yes, J. Yes, I. Cool. Any more? Yes, J? Uh-oh. No, J?
Once again.
Yes, Jay? Okay, cool. Wait a minute. Oh no, did they ask for components? The answer is yes, but what else did they ask for? Oh, how do we go from components to direction and magnitude?
You just put it on the
Yeah. What does this tell us, guys? Doesn't this tell us the over and the up?
Oh, yeah, just find the tangent.
So then use your little formulas to say, okay, u plus v, the sum of the two, is going to have a magnitude of and a direction of. Magnitude, what do? Pythagorean theorem. Someone start this one off. 33 point, use the full decimal, not the rounded one. Full decimal squared plus 53 point, the full decimal squared, square rooted. And as someone else, or as one person is doing that, or two people are doing that, How do we find theta? Look at your formula. Yeah, tangent inverse of, use the full decimal, 53.19 dot 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 over 33.04 dot dot dot. Magnitude, what do we got?
62.618.
Back them up, anybody? Square root of the 33.1 squared plus the 53.1 squared. Don't round until the end. No? Theta, what do we got? Tangent inverse of b over a. Caitlin's working on it, Alice is working on it. Nicole's just started. Ella, what have you done? She's still working. What is the tangent inverse for me? Alex, what do you have done? Oh, the magnitude? Okay, so I just got like that. Okay. Yeah, you're gonna have to do the other math to get the numbers, huh? Shai, have you done the angle yet?
How do you get that angle?
Tangent inverse of b over a, so the 53.19 not rounded, and then divided by the 33.04 not rounded.
I got the same.
Cool, 153? Thanks, Eris, Luda, Amanda, and the rest of you guys that were right behind. So we concur? So what was easier, having to set up with a few formulas and then just do some easy math? Or be super precise and use a lot of geometry and trigonometry? Yeah, most of us like that. And that's okay. Alright, get those answers down. If you guys need to catch up, you can go ahead and go back and double check, make sure with your calculator tonight that you can get there.
We all say those juicy.
That's a juicy problem. Uh-oh, it's about to get a lot more juicy. Why?
Let's do it like an example.
Whoa!
How about we do one from like homework?
Wait, we have been doing homework.
Dude, why do we need to go to college after we
Like
learn
number
all this?
91.
Oh, so
What's
it's number
college?
89?
Yeah, I got you.
What's
Got me,
USC
got
want to
you,
teach
whatever, we got each other. So, 89!
me? We need nothing more.
Oh man, what's going on this one? Let me see if there's a better example. Is that like 91? The incline?
It's a
Look at all
pulley
those
system,
angles.
and it comes down like this. This one's 50, this one's 30. They're pulling on a tube.
Oh yeah.
Those
It's hard, I understand. Okay, let's do this one, number 89. Kiddos, heads up. Okay, listen carefully. You saw me just go through 3 word problems, right, that I wanted to do examples on? We're going to try and get through 89, the setup. Tomorrow at the beginning of class, we're going to go through the next 2, but that means you should be able to get through homework all the way up until the word problems. Then I will give you the weekend to finish the word problems, but then we're going to actually start 6-4 for reals this time tomorrow. Sound good? So basically a day off. We'll do 2 more word problems, but oh man, you better do the rest of homework up until the word problems, or else you're really in trouble. Here we go. What do I see? Well, I see stuff going on the left, and I see stuff going on the right. Do you guys? I see stuff going on the left, and I see stuff going on the right. On the left, I see a vector showing the tension on the red crane. Oh, I should have done blue, shouldn't I? Because it's a blue crane. And then I have tension on the blue crane. Long story short, I'm pretty sure the box is too heavy for each of them to lift independently, but when they work together, they can lift it. Anyway, coming back. Find the tension. What are they talking about? Find the magnitude. We can call him V, and we can call him U. They're wanting us, when they say tension, they're wanting us to find, specifically, tension in each. Just to make it mathematical for you. They want us to find the magnitude of V, and they want us to find the magnitude of U. Does that make sense, kind of? And this one, the magnitude is denoting tension.
Are you given enough though?
Well, let's see. We're given two angles, that's good. But what else are we given that's hidden in the problem? I know it's the wrong color, but we have the other color being used for something else. Okay, so, well, it's kind of the right color. We know how many pounds the box is, right?
That should be a forced down.
20,000, yeah, exactly. So that's what's going on this way. So question, if we were thinking about a normal Cartesian plane, I know he's not in the sky, but we can think about him there, right? Okay. Then we could have our blue angle going like this, right? And we could have our red angle going like this. Is that true? I can actually get the angle. Oh my goodness, straw. Thank you. There we go. So we're going to go ahead and talk about vector u. We're going to talk about vector v. Let's start with vector u. Are we going to use the 24.3 if it's headed the opposite direction of my 44.5?
No, you're
No.
gonna use the
I'm going to use what he is in standard position. And kiddos, what would he be in standard position?
155.7.
Okay, so 155.7. Couldn't I do, for the horizontal components of u, couldn't I do, hold on, magnitude of u? Cosine of, what was it, Luca, 155.7?
Yeah.
Plus magnitude of u, sine of 155.7. Some of you guys see how this is going to get really messy really fast with all that magnitude notation stuff? Okay. Let's just call it then, for sake of simplicity. We'll call him X. How about that? Oh, you party poopers packing up? I'll make you all stay later. Wait, pack up, that's okay. But I'm just going to go ahead and as you guys pack up here, everything ready to go. What would we do for V? Pack up, it's okay. Some of you were about to jump out of your seats though, that's not okay. People started packing up early. Wait, how are we going to put both these vectors together? Add them, and what are they going to have to equal?
20.
This guy, that guy, that guy. Well, doesn't he have nothing happening horizontally? And he has quite a bit happening
What?
vertically. We'll talk about it tomorrow. All right, kiddos, get out of here. That's gonna be fun. Michael gets. Whose quiz was it?
Kenneth
I don't have a Kenneth.
I might be saying it differently.
And Eason? Can you take Eason? Eason has it? They haven't added it. No one's added it. Oh, Hi, Brandon.
I even checked the back to see if maybe, but there's a couple in here that don't have a back. Name on the back.
A couple people were absent, so they did one that I wrote for them.
It just seems fishy. That's all. Because she has one of the lowest scores.
But she was gone. Oh, stick on the